over the last 10 to 15 years, I've had several discussions with many forecasters, and all of them have told me pretty much the same thing, that you can't get good forecasts without good data. So I'm excited to present today someone who has spent over 20 years figuring out how to better develop better rainfall data sets. One of their latest data products that they developed, the CHIRPS Rainfall Archive, is now widely used around the world in research, monitoring, and early warning for many disciplines. Dr. Chris Funk is a federal scientist with the US Geological Survey. He is also a co-founder and director of the Climate Hazard Center at the University of California, Santa Barbara, where he has more recently been working with his colleagues there to bridge the gap between observational data and forecasting. Chris is now going to tell us how their pioneering work is going to improve our ability to provide advance warning of extreme precipitation and how his team is going about this. Colleagues, please help me to welcome Dr. Chris Funk.
Good evening, everybody. Well, before beginning, let me just, admit that most of our work and my research is focused on droughts. And so we're going to present some work that is relevant to extreme precipitation, but we're really not experts at this. And, so we're approaching this with a fair degree of humility. But of course, we think, like all of you, that extreme precipitation is a really important source of risk that we need to do better about managing. And it was really wonderful to hear Dr. Faka's talk and the great work that has been done recently. In this talk, we're just going to briefly go over different sources of predictive skill, strategies for integrating information from multiple sources, and opportunities for effective prediction and early warning to set the context. Then I'm just going to spend a few slides to describe the CHIRPS rainfall estimates and the GEFS weather forecast system. Then I'm going to describe how the Climate Hazard Center produces CHIRPS compatible GEFS rainfall forecasts, and provide 2 sample applications about how these can be merged together to provide effective early warning. So as you all know, there are multiple sources of predictive skill. And one of the most important, of course, is the ocean. Since sea surface temperatures change very slowly, they can be used to inform seasonal climate forecasts. And as we can see, this is from March 14th, and it was extremely warm over the Western Indian Ocean. The atmosphere can also provide a source of skill on 1 to 2 week timescales. Storms, heat waves, and rainfall deficits are also often predictable, which of course the E-Day was predicted very well, as we just saw. And then finally, the land surface. Soil moisture and vegetation extremes and deficits build up and persist over time, and this persistence supports predictions. We also know that climate change is exacerbating weather extremes by modifying these different components of the Earth system. In the ocean, exceptionally warm sea surface temperatures can drive terrestrial precipitation extremes and drought. In the atmosphere, warmer air can hold more water, contributing to more extreme precipitation events. And then in the land, over the land, a warmer atmosphere can draw more water from plants and soils, increasing the intensity of droughts. And as we've just seen, Southern Africa experienced really damaging floods as a result of recent precipitation extremes. So if we think about how we might take these different sources of information and merge them together, on the bottom here, I've put Dr. Faka's risk assessment, preparedness, prevention, and recovery. Before the event, we can use climate model predictions to provide alerts that might be quite general, right? Here, we're just sort of doing some contingency planning, saying, gosh, the Western Indian Ocean is really exceptionally warm. We might experience an above normal cyclone season. Then as we get into an event, we can use satellites to observe precipitation and quantify increased soil moisture and runoff, perhaps with a land surface model. And then we can also use weather model rainfall predictions to predict further increases in soil moisture and runoff. And the major theme of the talk is going to be to how to connect basically these two boxes, and then produce early estimates like our Climate Hazard Center early estimate that take both the observed rainfall from the satellites and the predicted precipitation from the weather models and merge them together. And then, of course, after the event, we might use high resolution satellite imagery. In this case, this is a detailed analysis of the flooding in Mozambique using Sentinel data to help guide recovery. Since I'm a drought guy, I couldn't resist putting in some examples from drought, and we might follow a similar sequence. So before the season, you know, the static climate forecast might provide alerts based on large-scale climate conditions, like it's an El Nino, watch out. Then as the season begins, we can use satellite precipitation observations like the CHIRPS to quantify early to mid-season rainfall deficits. And we might again use weather models to look out another 1 week or two to predict mid-season rainfall deficits. If we do successful intercalibration, we can combine these to provide joint outlooks that have both observations and forecasts within them. And then again, after the season is over, we might use high resolution satellite observations, like in this case, normalized difference vegetation index values to help guide recovery and assess losses. So now we're getting into the sort of data sets that we're going to be working with. Here at the Climate Hazard Center, we've developed the Climate Hazard Center infrared precipitation with stations. CHIRPS characteristics are that it is quasi-global over the land from 50 north to 50 south. It has a very high resolution for satellite precipitation, 0.05 degree by 0.05 degree. It has a temporal extent that is long from 1981 to now. And we produce it on daily, pentattle, decadal, monthly, 2 monthly, and 3 monthly timescales in lots of different formats. And there are two products. One is rapidly updated, the preliminary CHIRPS, and then once a month after we quality control all the input station data, we produce a CHIRPS final. And the basically the idea for the CHIRPS was originated at the SADC Regional Remote Sensing Unit, which had a similar product that they produced a long time ago. And that essentially inspired me to develop the CHIRPS. So you begin by creating historic climatology that we call the CHIP-CLIM, and you convert the infrared data to precipitation using a regression, and then you combine the percent anomalies of that cold cloud duration-based precipitation estimate with your climatology, blend in stations, and you end up with the CHIRPS. So I'm going to go ahead and go a little quicker. And we also are going to be looking at the, oops, did I just miss something? Yeah, so now we're going to talk about the CHIRPS gas blending. And for that, we're going to use the Global Ensemble Forecast System precipitation predictions, the National Center for Environmental Predictions Global Ensemble Forecast System. GEFS is a weather forecast system that provides daily forecasts out to 16 days at a coarse 1x1 degree resolution. You can see these on our Early Warning Explorer at the link there, and you can get this data from our FDP site. The GEFS forecasts have really high levels of skill. So this is for the first decade, first 10-day period of January. Here, with basically we're doing on a Jan 1st out the next 10 days, you can see you have really high levels of correlation. If we do it 5 days earlier, so basically when it's a further out forecast, the skill drops quite a bit. So really, for the next 10 days, though, you have high levels of skill. Here's another skill assessment for the 10-day period beginning on March 11th. Again, just showing that looking out in the next 10 days, we have a really high level of skill. So these are, really accurate. So if we can combine these accurate forecasts with our accurate rainfall estimates, then we can do a good job of informing early warning. So the way that we go about this, before that, the issues about combining these are that the GEFS is much coarser than the CHIRPS. And they have different mean values. And they also have different distribution characteristics. So here's just an example for East Africa. On the left is GEFS map for a given pentad, and the right is the CHIRPS. And so you can see they have really different spatial distributions. So the trick is, how do you go from the map on the left to something that has the same distribution parameters as the map on the right? Here's just a comparison of the 10-day GEFS precipitation values with observations from Ethiopia. And you can see there's some kind of systemic problems. It tends to have a lot of drizzle. So these are values that are very low in the observations, but have a lot of rain in the GEFS. And also, it tends to overestimate. So, if you have maybe 100 millimeters in truth, the GEFS might be predicting more than 200, which is a big issue. So we can correct a lot of these systematic problems by doing quantile to quantile matching. So if we have a value in the GEFS that might be a median value from the GEFS distribution, so the 50th percentile, we can go into the CHIRPS archive for that day, for that location, and find the corresponding value and make a map. Again, if we have a really extreme precipitation value, like say the 95th percentile value from the GEFS, we can go into the CHIRPS historical data for that day in that location and find the 95th percentile and make a map of that. Really, this is just all based on ranked data. So we can have ranked GEFS values for a given pixel in a given day, and we can find the CHIRPS values for that given pixel in a given day, rank them both, and just transform one to the other. So that GEFS values are replaced with CHIRPS values with similar ranks to produce the CHIRPS GEFS. So this is really simple but data intensive, but it works pretty well and allows us to stitch them together. So if we go back and we look at our raw GEFS values, and then we look at our adjusted CHIRPS GEFS values, we can see that, it's not perfect, but we reduced this kind of drizzle effect. And we also got rid of these spurious extreme values and increased our correlation and reduced our root mean squared errors by a lot. So it's pretty simple. It takes a lot of computing horsepower, but dumb, simple, and computing horsepower is one of the things our group is good at. So we're now just going to go over a couple example applications. We are producing now at our group these Climate Hazard Center early estimates that have observations combined with the GEFS forecasts. So we have either a CHIRPS final if it's available, otherwise we're using CHIRPS prelim, and then we combine it with our CHIRPS GEFS forecasts to provide seamless monitoring. And we're finding this to be a really effective tool. Again, it's really quite simple, but for a lot of things in the real world, this ability to cross between the observing and the prediction with these GEFS forecasts that have a lot of skill in the next 10 days or so is really powerful. And these are available via FTP and also in our Early Warning Explorer. So here's an example that would be relevant to the flooding that happened in Southern Africa. And so if we're on March 7th, we could take the last 10 days of the CHIRPS observations plus the next 10 days of the CHIRPS GEFS and produce a map that looks like this, where we're finding predictions of really extreme events over central Mozambique and Malawi. Didn't really do a good job in Zimbabwe, and of course on the eastern coast of Madagascar. So this is a tool that could be used to provide early warning. I have to say and admit that we are still having issues with the chirps itself. It probably does not represent really well extreme precipitation events because it was designed for droughts. We're working on that. But at least as a first cut of providing an outlook of incoming really heavy precipitation, this would be a useful tool, though I would say it would probably tend to underestimate perhaps some of these extremes, as I think Tamuka found looking at the chirps values in March. Then again, we can have just one drought example. And again, this is from February 2nd of 2019. And we might take 31 days of the chirps values, which would be January, and then 5 days of the chirps guess forecasts to produce a Climate Hazard Center early estimate of forecast climate anomalies, precipitation anomalies. And again, this shows this really widespread drought over Zimbabwe and southern Zambia. That is a big issue now in terms of potential rising prices and food deficits. So these are two just simple examples that show the utility of combining observations with forecasts. And by integrating observations and forecasts, we can improve effective prediction and early warning. Using quantile matching, we can improve the performance of the GEFs and support seamless integration with chirps. And the Climate Hazard Center early estimates provide a useful example of such integration. Thanks a lot.
Thank you very much, Chris, for sharing that. I think we got a very good overview of the work that the Climate Hazard Center is doing, integrating the forecast data from the GEFs with the chirps data and producing an improved forecast from that. Do we have any questions for Chris at this moment? Looks like there are no questions. Chris, I have one question for you. In terms of how do you see the improvements that might be made in terms of the ability of the chirps to better estimate extreme precipitation events? Do you have anything which is already on the cards that you're planning to try out in terms of your research on that?
Yeah, thanks, Tamuka. Yeah, there's sort of two things that we have in the works. And one is chirps 2.1 revision that should be available by the end of the summer. And that'll be a relatively minor change in the chirps, but that should improve things. And in that revision, there were some places in the chirps process where we put some kind of caps on the different kinds of rainfall perturbations that we use. Let me just go back here. Yeah, like this percent of normal, for example, precipitation change. I think that is capped to be no greater than 3. So, you can only be 300% of normal when we produce the chirps 2.0. And there's a similar kind of thresholding when we blend in the stations with the chirp. And in the revised chirp 2.1, those thresholds will either be removed or greatly increased. So that should help. And then soon, but not very soon, we're going to do a chirps 3.0, which will be a major rewrite of the chirps algorithm, in which we're going to modify the way that the ChipClim is used, so that when we see signs of really heavy convection, we're going to increase this ChipClim value. So we know that we have issues when ChipClim is really low and we get a tropical cyclone, right? So for example, if you're in Yemen, which is climatologically really dry and ChipClim is almost close to 0, and you have a tropical cyclone come through, which happens, it's really hard for the current chirp to represent that well. So we're going to look at some ways to modify the ChIP-CLIM conditional on the large-scale climate. But that's a big advance in a big research topic that's going to take us, probably a year or so to work out.
Well, thanks for sharing that. We look forward definitely to those improvements. But in the meantime, already, ChIROPS is already a very useful data set for drought analysis. We have another question here from Dr. Alindo. Two questions, actually. One is saying, how do you compare ChIROPS with other satellite products, e.g. ARC? And I'll just give you both questions at the same time so you can work through them. The second question is, how do you deal with reduction in MET stations, especially in Africa?
Yeah. Okay. Well, so for the first question, there's one paper by Dr. Tote et al., T-O-T-E, that does a comparison of these different products. I think over Madagascar or Mozambique, that you might look at. I can send that around. But in general, the IR part of the ChIRP is quite similar to the ARC2. So in kind of percent anomaly space, they're generally quite similar. But a lot of studies, basically almost all studies, show that the kind of mean performance of the ChIRPs is better because it's built around this high resolution climatology. Though that can, as we just discussed, sometimes get us into trouble when looking at precipitation extremes when the climatology is really low. And then one big difference between the ARC2 and the ChIRPs data set is that the ChIRPs, especially the ChIRPs final, incorporates a lot more stations. So, for example, for Southern Africa, we include the SASCAL precipitation values and the Global Historical Climate Network and Global Summary of the Day. So they're relatively similar, but honestly, I think that the ChIRPs tends to perform a little bit better, though it also has longer delays. So, there are relative strengths to both products. And then the second question regarding the eroding station network in Southern Africa, or in general in Africa, which I think we agree with probably everyone here is a big problem. The ChIRPs is really resistant to those issues associated with the decay and changes in the station network. And that's really by design. So essentially, when we get to this ChIRP, okay, by construction, we end up with something that has a mean that tends to be really close to the mean of the stations. And so that makes the ChIRPs relatively resilient to changes in the station networks over time. I'm not saying it doesn't have any effect, but if you compare how the ChIRPs process blends in stations with how the ARC2 blends in stations, they're very different, and we know that the ARC2 is much less resilient to changes because the ARC2 cold cloud duration estimates have a lot of spatial bias in them. I don't know if that answered the question, but we take that really seriously, and we think we do really quite a good job of making the ChIRPs relatively resilient to changes in the network over time.
Yeah, thanks for that response, Chris. It's interesting to note that I think Dr. Faka also mentioned something similar with the problems with the low density of stations and even the decrease over time as well. So it's interesting to note how the ChIRPs can really help to try and alleviate that, while we will still continue to hope for increases in the station network, especially with the increase of the number of projects that are bringing in automatic weather stations. I think I've got one last question here from Simon. where he's saying, thanks for the presentation. The final product depicted the drought situation over Namibia very well. And his question is, what is the maximum period available for drought monitoring? And his second question after that is, does the product depend on the weather focused model?
Okay, let me answer the second question first, which is that, yeah, it's all, I mean, we're just building this around the GEFS weather forecast model. In theory, it could be applied to any model, but that's the one that we're using. So it's quite model specific. Tamuka, do you think it's okay if I just show the FTP site? Do we have time for that to answer the first question?
Yeah, sure. You can show it in 30 seconds. Yeah, that's all right.
30 seconds. Okay. Okay, so let's see if this will come up. Can you see, are you seeing my? So the early estimates are produced by a great graduate student we have, Will. And so we're in the FTP site under People Will, under the CHC early estimates. And we can go to Africa. And then there's both graphics and data. So you could actually grab all this stuff in a data format and make your own maps or do your own analysis. But so this has just been updated yesterday. And so basically you can see that Will is making different accumulations for 5, 9, and 15 pentads for Southern Africa. And I'll just leave it at that, but those are breadcrumbs to get you guys to find the path to the data and the graphics.
Awesome. Thank you so much, Chris.